All right. Bismillahirrahmanirrahim. Let's begin where we left off last time. We were talking about corner detection. Okay. And I motivated corner detection by saying that this is like an essential step in, let's say, trying to make a panorama, and so you have to figure out the homography between two images. Okay. So the first step to do that is to find some points in one image, to find some points in another image. These are local features. These are features which are based on a small neighborhood of the point where you are finding them. And we saw that local features should be repeatable, which means in the second image I should get them at the same place, and they should be distinctive so that I can match them properly. And so we saw some interesting properties of those features. Okay. Now I'm going to motivate a simple corner detector, which is like a nice small quick corner detector that you can build. Okay. So my question in motivating this is that how would gradient vectors look like in the vicinity of a corner? We looked at that last time. So here I have a synthetic image changing kind of smoothly from black to white. Okay. And I want to know what is the characteristic of the corner here. So if I'm on a flat patch, then my gradient vectors within this patch, if I look at all the gradient vectors and see how they vary, they're not going to vary much. In fact, they're going to be close to zero. Okay. So gradient in a smooth region is close to zero. Gradient along an edge, if I look at this patch and look at all the gradient vectors in there, I will see that they are high in one direction but not high in the other direction. Okay, so gradient vectors in an edge are all pointed in one direction, but gradient vectors at a corner are pointed in more than one direction. So if I have this patch, this third patch here, I will look at the variation of gradient vectors within this patch, and I will realize that they are actually pointed. Excuse me, Shara. What's going on? Yeah. Okay. So we are. So we look at the gradient vectors in this patch, and we see that they will have more variation. They are not just all pointed in one direction. They are pointed in. They have derivatives in multiple directions. Okay. So the nature of variation of the gradient vectors in a small neighborhood can be an indicator of whether it's a good corner or not. Okay. And we are interested in corners. When we want to do point-by-point matching, we are interested in corners rather than flat patches or edges, because flat patches or edges do not give us good localization. They do not tell us exactly where a point matches. Right? Everyone understands that? Okay. So how can I use this idea to build actually a algorithm to find that? So the nature of variations of gradient in a small window is an indicator of cornerness of a point. We have kind of established that, right? I have to look at, if I want to say whether this point is a corner or not, I'll look at a small neighborhood around that point, and I'll try to see how the gradient vectors vary in that. Now, how do you find the variation in some data? Okay, the derivative of a gradient will be rate of change. Yeah, that's possible, but here you will have to do some sort of direction thing, that the variation that you want to see is in the direction. But in general, if I give you some data, how do you measure variation in it? What are some measures of variation? The variance of the data itself is so if I give you let's say the data of height of students in LUMS, okay, and you want to see how homogeneous the height of students in LUMS is, the way to do that would be to look at the variance of that height data, and if the variance is high, then LUMS has a lot of short students and tall students, and if the variance is low, then they are pretty much homogeneous in their height. Okay, so how do we measure variations of any data? Well, variance is one measure of that. How do we measure variations of the gradient vector? So for one-dimensional entities, which are not vector scalars, variation is measured by variance, right? Now, what is the definition of variance? The variance of a variable x, it's a random variable, so x will take on many different values, is the expected value of x minus the mean of x, which is the expected value of x, square of that. So the expectation of x minus expected value of x square, that's by definition variance. Okay, you have seen this before in statistics class or so on. In fact, you might have also seen this, that it's mathematically equal to write variance in this form. Oops, ink on off, but ink is disabled. Why is ink disabled? Okay, we'll worry about that later. Okay, so you can have variance in this form, but this is mathematically equivalent to this form, which means you can just find the expected value of x square without subtracting the mean, and then subtract the square of the mean. These are both equal, and you can just expand out this expectation. First, expand the square, okay, because there is a square function, so a minus b, which is a square minus 2ab plus b square. So expand that out, then expand the expectation into that, and then you will be able to see that it's actually equal to this. Okay, all right, but this is for one-dimensional entities, so gradient is a two-dimensional vector. So how do you measure variance of a vector entity? Okay, so what you are saying is you can separately measure the variance of the x component and the y component of that entity, but that actually doesn't give you the complete picture of variance, because we don't know whether x and y are independent of each other or not. If they are independent of each other, you'll get like zero covariance between them, but if they are dependent on each other, you'll get a non-zero covariance term between them. Okay, so this is also a topic from probability and statistics, that for vector entities, how do we talk about variation of an entity? We talk about the covariance matrix. Okay, and so here we have a 2 by 1 vector. Okay, so I really need a pen now. So okay, good. So here we have a 2 by 1 vector. So the definition, what happened? Where did my pen go? So covariance of a vector, this is equivalent to, if it were a scalar, I would say variance, is the vector times its transpose, the expected value of that, which means x will take on many different values. So you will take each value, each gradient vector, multiply it to its transpose. Now the gradient vector is 2 by 1, so its transpose is 1 by 2, so you get a 2 by 2 matrix. And in fact, what you will get is a 2 by 2 symmetric matrix, because it's XX transpose, so it's an entity multiplied by itself, so that always results in multiplied by its own transpose, so that always results in symmetric matrices. So you take the expectation of that, which means you average that out over all possible x's, minus the expected value of x, that's just the average gradient vector, times its own transpose. Okay, this formula is kind of equivalent to what we saw before, except you had x square here, right? So as a scalar you had square, so as a vector you have xx transpose. Okay, so really the picture here is that you will have a vector like this, 2 by 1, and you'll multiply by its transpose, 1 by 2, so you'll get a 2 by 2 matrix. Now what will this value be? This value will be the expected value of just the first term. So it will be expected value of x square minus expected value of x, if x is the first coordinate, square. And what will be this value, the 2 by 2 term? This will be expected value of y square minus expected value of y whole square. Okay, so this is really the variance of x, sigma x square. This is really the variance of y, sigma y square, Uh, but what you have, but what you have on the diagonal is what is termed as the covariance. It's actually something proportional to the correlation between x and y. So if x and y are completely uncorrelated, what does it mean x and y are uncorrelated? It means if I tell you the value of x, if x is high, you can't tell me anything about y, whether y is high or low. That would be uncorrelated x and y. Okay. So if they are completely uncorrelated, then you actually get a 0 here, and by symmetry you get a 0 here. But if they are correlated, actually what you get is the correlation coefficient times the standard dev of x times the standard dev of y. That's really the covariance term. Okay, I'm just reviewing that from a probability and statistics course. How do you talk about variance of random variables, which are vector random variables? But this is what the definition of covariance is. Okay. All right. So the term that I have here is the mean gradient vector times its own transpose, which means within that window, let's say that window was 10 by 10, so I have 100 gradient vectors inside it. So I just average them out. That's expected value of x. Okay. So what's likely to be the mean of a gradient vector? In general, if I had lots of data, lots of gradient vectors in the world, if I average them out, what am I likely to get? What's like the average gradient direction for a picture or a database of pictures? Yeah? No? Sorry? 0. Why 0? Yeah, so if I assume that there is no preferred direction in the world, which by the way for natural images is not true. A lot of images are outdoor photographs which have a horizontal line passing through them for the horizon and so on. But if I'm just loose about it and I take a hand waving argument, there's no preferred direction in the world, right? I could have a gradient vector with equal probability. I could have a gradient vector pointed this way and that way and that way and that way. If I assume that the direction of gradient is uniformly distributed, then on average my gradient vector should be 0. Now this is a loose hand waving argument that I'm building here just to motivate the expression that I'm going to use. There are other better reasons to use this expression, but I'm motivating it from the variance point of view specifically. Okay, so I'm going to just loosely assume that in general gradient vectors are 0 mean, because they could be pointed in any direction. So vectors in this direction would cancel vectors in this direction when I'm averaging them out. So in general they are 0 mean, and therefore I'm going to drop the second term, and I'm going to say the covariance of x. Well, this is in general true. If x is a 0 mean vector, then covariance of x is just equal to expected value of x transpose. Okay. For those who have taken signal processing, there is actually a better argument to talk about this entity, which I've motivated it from variance, but this is actually the autocorrelation function of x, which is a better argument, but then I'll have to go into what is an autocorrelation function, so I sidestepped that. I like it to be motivated more from variance. I'm just saying this is covariance of x as long as x is 0 mean. Okay. All right. So that simplifies my expression a little bit, and then so the covariance of the gradient vector, the gradient is instead of x, I'll just put the gradient vector. So the covariance of gradient of ixy is approximately equal to, assuming that gradient is 0 mean, it's actually equal to the partial derivative with respect to x squared summed over, right, the whole patch that you have, the partial derivative with respect to y on the diagonal term squared, and the off diagonal terms are the partial derivative of I with respect to x and the partial derivative of I with respect to y. What is this summation over? This is over whatever window you are computing this gradient entity. Okay. Everyone understands this expression, because what was the gradient of I? It was partial derivative with respect to x, partial derivative with respect to y. So I just took its own transpose, and then because of the expectation, the summation is coming in. Yeah. What is? I is your image pixels, the actual pixel values at location x and y. Okay. So the gradient of I is the partial derivative of I with respect to x, which is what we saw last time, the x gradient, and the partial derivative of I with respect to y, which is the y gradient. Okay. So this matrix, this 2 by 2 matrix, is kind of, I can think of like the covariance matrix of the gradient vectors if they are zero mean, and so this matrix really is a measure of the variance of gradient. And since I said that the variance of gradient is going to tell me whether a patch is a point, a corner, or a edge, so really it should be this matrix that should tell me whether a patch is a flat region or a edge or a point or a corner, right? Everyone follows that argument? So what I showed you on the last slide, I said it looks like variance at a corner gradient would vary differently. Now I've written a mathematical entity, and I'm saying at a corner this mathematical entity should have a different form. Okay, so for simplicity of notation, instead of partial derivatives, I'm just using subscript x and y here. Okay, so I sub x is the partial derivative of I with respect to x, and I sub y is the partial derivative of I with respect to y. Okay, so this is what the covariance of gradient looks like. And this matrix tells us about the variation in the gradient vectors in a window, in a patch. Okay, so if I want to find corners, the strategy I'm going to do is I'm just going to take a sub window, slide it all over the image, and at every location where I get that window, I'm going to find this matrix, and then I'm going to do something with that. Okay, I'm going to decide by looking at the values of this matrix. I'm going to decide, well, that looks like a corner. Yeah, maybe, because for edges it will have some specific form, but edges is actually easy. I don't really need to look at the variance. I can just look at the gradient value itself, and that tells me the edges. So I really don't have to look at the second order statistic to find edges. Variance is a second order statistic, mean is a first order statistic. So yeah. We're going to do exactly that. We're going to slide and do a sum of square differences type of strategy. Yeah, we're going to do exactly that. In fact, we're going to slide and just compute this matrix. This matrix can also be derived by doing sum of square differences and writing it as a least square solution, and then solving. So there is a different derivation of this matrix also. Yes. It will tell me something about the variation of the gradient vector. I'm saying I can do this after class if you're interested, but I'm saying if I did it the other way, like I showed you the tree image, and I said I was computing the sum of square differences, and it looked like a different type of surface, I could write that surface, take the Taylor expansion of that expression, the sum of square expression, and actually I'll end up with the same matrix as the first order term in a Taylor series. So there are different ways to describe this matrix. In fact, this matrix is very important. It appears in many different problems in computer vision. If we study optical flow later, we'll see that the same matrix appears there. Okay, but one way, my preferred way now to look at this matrix is as a covariance matrix of a zero mean vector. Yeah, let's skip that for now. Assume you have a good window size. That's an issue of scale. I'll come to that. Okay, so now let's look at this matrix and try to build an understanding of what this matrix looks like for different types of cases that we might encounter. So if we have a flat patch, what would be this matrix? All zeros. Yeah, that makes sense. All zeros, because the gradient is all zero. So the x derivative is 0, the y derivative is 0. I sum up a bunch of zeros, it's still 0. Whichever way I look at it, it's 0, right? I multiply 2 zeros, it's still a 0. So it's all zeros. So that's not a big deal. So on a flat patch, this matrix will be all zeros or very close to zeros. It will be very small numbers. On an edge like this, it's a vertical edge. So what will this matrix look like? Which way is y? Y is going that way. So when you do the y derivative, you'll get a high value, okay, non-zero. When you do the x derivative, you'll get a 0 because there's no variation in x. What about the off-diagonal term? What about the covariance term? Covariance will be 0. Why? Because you have a product there of x and y variances. I mean the square root of that. So you have a product of x standard dev and y standard dev happening there. So or let's look at it just from this form. You have a product of the x derivative and the y derivative happening here. So the x derivative, if the x derivative is all zeros and the y derivative is whatever, the sum is going to be still zeros. Okay. In general, actually, for any data covariance, if you have two variables, and those variables are uncorrelated to each other, okay. By uncorrelation, what do I mean by correlated variables? Correlated variables are like, what example should I give? The height and weight of a person. Okay, so I make a vector where the first value is height and the second value is weight. Okay, now this data, my claim is it's correlated. It's not perfectly correlated. There are some short people who are very fat, and there are some tall people who are very thin. Okay, so it's not a perfectly correlated data, but there will be some correlation, some positive correlation, because generally if a person is taller, their weight should also be higher. Okay, even if their waist is the same, it will still be higher because they have more span. Okay, more volume. So if I plot that data, okay, on this new computer I still have this problem. So if I plot that data of the height and weight of LUM students, okay, so here I have height and here I have weight. So what will I get? I'll get some sort of trend which is broadly like this. Oops, sorry, I should be drawing dots. So I'll get some sort of trend which is broadly like this, but there will be some points here, some very tall people who are, oh, no, not that low on the axis, okay, some very tall people who are low weight, and some very short people who are high weight. So I'll have something, but this data does have some sort of trend. Okay, so this is positively correlated data, which means, how do I know it's positively correlated? If I tell you nothing about a person except their height, I say this guy is very tall, you can make some general statement, some approximately correct statement about their weight. They are likely to be at least 80 kg. Okay, because the guy is very tall, he should have somewhat of that weight. So you have this relationship in your mind that if variable x is high, variable y will generally be higher. It will not always be higher, but statistically it will generally be higher. Okay, so that's positive correlation between data. Correlation coefficient is a number that varies from -1 to 1. So this correlation will be like maybe 0.3 or 0.5 correlation. Okay, if I have +1 correlation, that means a perfect linear relationship, a perfect linear positive relationship. You tell me x, I'll tell you y exactly. That's a linear relationship. But a correlation of 0.5 means I can tell you y approximately if you tell me x. Okay. A negative correlation means the variables have an inverse relationship between them. If x is high, y will be low. Negative correlation of 0.5 means if x is high, I can tell you that generally y is low, but negative correlation of -1 means a perfect linear relationship with a line of slope which is negative. So you tell me x, I'll tell you y exactly, as a but y will decrease when x increases. Okay, so correlation of 0 means you tell me x, I can't tell you anything about y. Okay, and that's why you can see that from here. If I tell you this coordinate, you can't tell me anything about that coordinate because it's an axis aligned feature. So I don't get any information about the second axis. Okay, if this edge was going on a diagonal, then if I tell you that I have a point along the edge where x is high, well, that means y should be higher also. Okay, but in this case, if I tell you x value, you can't tell me anything about the y value. Okay, all right. So we saw that the matrix in this case will be, the off-diagonal terms will be 0 because data is uncorrelated, its axis aligned. One of the diagonal values will be high depending on which one is your axis, which way is your axis going. One of the diagonal values will be high and the other one will be 0. Agreed? All right, so what about this? Well, that's like the same except the two values will be flipped. So the other one is high and the first one is 0. Okay, what about this? Yeah? Okay, so in this case, the Ix variance will be high, right? The derivative with respect to x is high because there is some x derivative, and the derivative with respect to y is also high because there exists some vectors which have very high y derivative here in this case. So the diagonal terms are higher, but the off diagonal term, well, even though x and y are both high, but still my features are axis aligned, and so the off diagonal term is still 0. Okay, this is uncorrelated data. So the argument here is from correlation. It's actually difficult to see from multiplications how come those things will multiply and add and I'll get a 0, but they'll multiply and add in exactly uncorrelated fashion that I'll get a 0 because the correlation coefficient here is 0. This is an axis aligned feature. Okay, one way to see this is that the result of this should be some sort of sum of the results of these two. Okay, so that's like one argument that you can have, even though that's not exactly correct, but almost correct. Okay, all right. So now, but things get interesting. The patches that I get in my images will not be always aligned with x and y directions. The feature could be in any orientation, like an edge going in the room like this and so on. Okay, so what will be the covariance matrix of this edge? All four will change. Okay, what will happen is that I have some x derivative because if I move in the x direction, yes, I do encounter a change. So I have some x derivative. It's not 0. I have some y derivative because if I move in the y direction, it will change. And since this feature has an orientation, I have actually a relationship between x and y. If you tell me the x derivative, I can tell you something about the y derivative. The x and y derivatives are actually related to each other here. Okay, so I have an off diagonal term. In fact, my correlation coefficient would be non-zero here. Okay, because I have a correlation between my x and y values. All right. So this edge for this matrix will look like there will be values all over. Okay, and what about this? Here also, I have some x derivatives, I have some y derivatives, and in general, my off-diagonal terms would be non-zero. So here also I get 4 non-zero values. There are really 3 because one of them is symmetric, but I mean, all 3 of them are non-zero here, and in this case, all 3 of them are non-zero here. Okay? Is that argument clear? Yeah, question? In last two, all values are non-zero. Oh, here? Okay, so here I'm saying, okay, so I'm saying for this case, the off diagonal term will be 0. Okay, why? Because this is an axis aligned feature. For this case, the off diagonal term will again be 0. Why? Because this is an axis aligned feature. Okay, so there is no correlation between x and y values, between the first and the second values of the gradient vector. I'm saying this case is kind of like a combination of those two cases, so the same argument holds. The x derivative exists, the y derivative exists, so both have some variance, but the off diagonal term, because this corner is axis aligned, will be 0. Okay, but in this case, that's not, as soon as I rotate these features, the values change and the off diagonal term becomes non-zero. Okay, all right, so so this I did just for you to build an understanding of what the covariance matrix looked like, what this matrix would look like, right? So now this matrix would have been a very good corner detector, except for this guy here, this messed up, right? Because if this wasn't the case, I would have a very simple corner detector strategy. I would say, if I have x and y variance in both directions, then it's a corner. And if the off diagonal term is non-zero, it's a corner, or it could even be 0, then it's an axis aligned corner. But in this case, I get x and y variations in both directions, and I get some off diagonal term 0. So it's difficult from looking at those values to distinguish this guy from this guy. That's really the problem. If I can do that somehow, then I would be okay. I'll have a corner detection strategy. Okay. Okay. So one strategy is actually straightforward from this slide. What I can do is, I will be given a patch, and I'll compute this matrix for that patch. Okay. If that comes out to be all 0, I'll discard it. It's just a flat patch. It's not of any interest in corner detection. Okay. If I get only one value non-zero and the other 0, I will know it's an edge. Okay, so I will discard that also because I'm finding corners. But the complicated case is when I get all non-zero values. Okay, now there is a strategy where I can disambiguate between these two bottom cases. What I'll do is I'll start rotating this patch. Okay, and keep computing this covariance matrix that I have. Okay, so I'll rotate it. As I rotate it, these values will change. If once I get to one of those rotations should be such that the off diagonal terms come out to be 0, because at some rotation the feature within this patch will become axis aligned, and at that the off diagonal terms will become 0. Okay, that's theoretically that's always possible. Actually, you have a covariance matrix from the rotation of the data. The covariance matrix can become decorrelated. Okay. Which means the off diagonal term is 0. Okay, so once I do that, I will just look at the two diagonal values, because the off diagonal terms have become 0. I'll just look at two diagonal values. Are they both significantly large? If they are both significantly large, I have a corner. If only one of them is large, the other is very small, I have an edge. Yeah? Forget it. There's no problem with curved edges. You still get a matrix like this, and it can still be decorrelated. So it's a 2 by 2 matrix. I've just shown you very corner cases, but it will find, it's just looking for variance and gradient. So there's no problem with that. Yeah. Yeah, I try a lot of rotations. I'm not going to do that. It's an incredibly expensive algorithm, actually. Think about, my image is 1,000 by 1,000 pixels, and the corner could be anywhere, and I'm trying all possible windows. That alone is a lot of work. And then each window I'm going to like rotate it and see whether it became 0. So it's actually a lot of work. Okay, so I'm not going to do that. But I'm just saying, if I had the luxury to do that, I will have a corner detection algorithm. Agreed? Is that argument clear? All right, good. So this is the two covariance matrices that these are the two cases that I want to distinguish between them. So now I'm going to use some mathematical property that will actually allow me to not rotate and still get to that case. Okay. So, well, the covariance matrix has some interesting properties. Number one, it's semi-positive definite. What does that mean? No, not exactly. The definition of semi-positive definite is that if I have any vector x transpose and this matrix is A, then x transpose A x will always be greater than or equal to 0. That's a semi-positive definite matrix A. The other definition of that could be that the eigenvalues of this matrix are always going to be either 0 or more than 0. They can't be negative. Okay. So this is I mean, we can prove that this is a semi-positive definite matrix and its eigenvalues will be non-negative. Okay. What are eigenvalues? We have done that before. An eigenvector is a vector such that which does not rotate when the transformation of that matrix is applied. Ax is equal to lambda x. So x does not rotate. It can only scale, but it does not rotate when A is applied to x. Okay. All right. So if the x values do not tell me anything about the y values, then the off diagonal terms are 0. That's this case. Now, the other cases that I'm interested in are rotations of this case, right? Because I said I can rotate all the cases and figure out whether I get the off diagonal terms to be 0 or not. Well, the interesting thing is that what happens to the covariance matrix, let's call that A, what happens to A when I actually rotate the image patch? How does A rotate? Now my claim is, and this is like the crux of the whole algorithm, my claim is that if I rotate the image by R, okay, if I rotate that image by R, then the covariance of the gradient changes by R transpose. You understand what I'm saying? I have a patch, I have gradient vectors in it, and I can find the covariance matrix of those covariance matrix, no problem, right? Now I rotate the patch, I give you a 45-degree rotated version of it, and I say compute the covariance matrix. You can do that again, take all the vectors, they will all now be rotated, right? They will all now be rotated, and you compute the just a second, I'm getting this code again. Okay, so all your image is now rotated, so all the gradient vectors are also now rotated. So you can compute the covariance again if you want to, but I'm saying there should be some relationship between the covariance of the rotated part and the unrotated part, because the covariance would change according to some rules, right? And my claim is that if I rotate by R, the covariance A changes by R transpose, where R is a rotation matrix, cos theta minus sin theta cos theta. Okay, yani you do not need to recompute the covariance. You can just know that, okay, I rotated by 45 degrees, so the covariance matrix you can adjust by 45 degrees using this formula. Okay, you understand my claim, right? I'm going to prove it, right? It's a straightforward proof actually. What is A? A is the expected value of gradient of I transpose. Because I'm assuming 0 mean, so I didn't have the other term, so that's exactly what A is. Okay. Now I'm going to rotate the image by R. Okay. So after rotation, the gradient becomes R of gradient of I, because when I rotate, the gradient vectors are all going to rotate. So it's just rotation applied to those gradient data. So the rotated part after rotation is R gradient of I transpose, the expectation of that would be the variance of the rotated image, the rotated gradient. But since R is a constant inside expectation, it's not a random variable, it's a constant, I can move it outside the expectation. Okay, so that's equal to R times the expected value of gradient of I transpose times R transpose. Okay, and the expected value of gradient of I transpose is nothing but A. So I get R A R transpose. Is that proof clear to everyone? Yeah. The A B transpose is equal to A B transpose. So here A B transpose is equal to B transpose A transpose. So I get del I transpose in here, and R transpose I took out of the expectation because it's a constant. Yes. So very simple, elegant proof. Which means what I was saying was that I would need to rotate this image and keep rotating that till I find that particular covariance on which the off-diagonal terms are 0. Then it becomes that first row of cases that I showed there, and I can tell whether it's a corner or not. But it turns out that I don't need to rotate the image. I can just rotate the covariance matrix itself, because I know how to apply the rotation on the image such that, directly compute the rotated covariance. Let me call that A prime. So I can directly compute A prime. Okay. So okay, that should be nicer, because I don't need to try a lot of rotations on the image data itself, recompute the gradient vectors, and then compute the covariance again. I can just apply R on the covariance. That should save me some work. Yes. Let me just continue and we'll see something. I'm going to do something more. It's still a lot of work. How many R's am I going to try, right? 1 degree, 2 degree, 3 degrees, all the way to 360 degree. How many R's am I going to try? So let me consider something more. There's like a neat, elegant trick to find the correct R, which will decorrelate the covariance matrix, which means by decorrelation of covariance matrix, I mean the cross correlation terms, the covariance terms become 0. Okay. So to be able to do that, consider the eigenvectors of A. I'm now talking about the eigenvectors of the covariance matrix. Okay. Let's say that phi is an eigenvector of A. Phi1 is one eigenvector of A, and phi2 is another eigenvector of A. कौन? अभी नहीं आ so consider an eigenvector of A and another eigenvector of A. Okay, so there's a phi1 and a phi2, which are two eigenvectors of A, and lambda1 and lambda2 are two eigenvalues of A. Okay, so this is just by definition. I'm just considering eigenvectors of A. Let me call them phi1 and phi2. Then this relationship should hold. Agreed? I'm going to write this relationship as one matrix relationship. I can combine these two equations into one equation. I call it A phi is equal to phi lambda. Okay, where phi is phi1, phi2. It's the matrix of eigenvectors, and lambda1, lambda2 on the diagonal is this cap lambda. Okay, you can convince yourself that this one equation, this one matrix equation, is exactly equivalent to these two non-matrix equations. Okay, I just have to write lambda the other side so that it multiplies by columns, not by rows. If I had lambda on this side, it will be multiplying by rows, but I wanted to multiply by columns because I wrote the columns as eigenvectors. Okay, this is something we did in the tutorial actually, but I'm doing this again. So it's just a straightforward way to combine those equations. Just expand this and see, it will come out to be both the same thing. Okay. Where phi is an orthonormal matrix of eigenvectors. Why do I say that? Eigenvectors do not necessarily have to be orthonormal. Okay. Well, one thing, they don't have to be normal. They could be longer than one. Their length could be longer than one. But if that is the case, I can always normalize them, and whatever is that scale factor, I can put into lambda. So if you give me an eigenvector which is not of length 1, I can always give you an equivalent eigenvector which is of length 1, and correspondingly just the appropriate lambda. Okay. And then in some cases, like the identity matrix, like the Cartesian axis, the eigenvectors do not even have to be orthogonal. If you give me a matrix 1, 0, 0, 1, any vector is an eigenvector of that, right? So I can have eigenvectors for that which are non-orthogonal. But if such a case exists, then I can always find a set of, that means there will be a lot of eigenvectors for this case, and I can always find one set which is orthogonal. Okay, in this case 1, 0 and 0, 1 are two orthogonal eigenvectors, or 1 over square root of 2, 1 over square root of 2, minus 1 over square root of 2, 1 over square root of 2. Those are two orthogonal eigenvectors of the identity matrix. Okay, so the bottom line is, even if you give me eigenvectors which are non-orthogonal for a covariance matrix like this, I can always orthogonalize them, and I can always normalize them and have an equivalent eigenvector eigenvalue. So therefore I will assume that phi is always an orthonormal matrix. In fact, that's what MATLAB does. In MATLAB, when you say eig of something, there are a lot of possible eigenvectors pairs that MATLAB can give, but MATLAB returns you an orthonormal matrix as eigenvectors always. And then whatever are the corresponding scale factors, it put into the lambda matrix. Okay, so therefore I'll assume that phi is an orthonormal matrix of eigenvectors, and lambda 1, lambda 2 is a diagonal matrix of eigenvalues. Agreed? So this is just the covariance matrix eigen decomposition. This equation 1 is just the eigen decomposition of the covariance matrix. All right, so what is the inverse of an orthonormal matrix? It's a transpose, right? So which means I can take phi on this left hand side, multiply with its transpose, post multiply by phi transpose, that will be identity, and I'll get a phi transpose there. So that means phi transpose A phi, actually from the right hand side I'm moving to the left hand side. So phi transpose A phi is lambda, right? No big deal here. And lambda is a diagonal. This is the last step that I needed. Because what does this mean? If I form a rotation matrix which is phi transpose, if I form a rotation matrix from the eigenvectors, then that will decorrelate my covariance matrix directly. I don't need to search all over. Okay? So this implies that rotating the image by phi transpose diagonalizes the covariance. Now, so that's really cool, right? Because once I diagonalize the covariance matrix, which is actually nothing but the eigenvalues of that of the covariance matrix, right? So eigenvalues of that gradient data that I had, the covariance formed out of that. So once I diagonalize that, that is the actual covariance matrix of the axis aligned version of this data, the decorrelated form of this data, which means I've now reduced those 5 cases that I showed you. There were 6 cases. There were 4 on the top row, and there were 2 in the bottom row, and the 2 in the bottom row were the problem. But now I have a tool to always convert those 2 in the bottom row to the 4 in the top row. All right? Yeah.
For rotation matrix, the redundant has to be +1.
Yeah.
How do we make sure that?
Yeah, you can just, if it's not, you can just flip the order of phi 1 and phi 2. It's arbitrary, right? Which one I call phi 1 and which one I call phi 2. So you can always do that. Or you can think that it's a rotation and a reflection. Even that doesn't do anything to this treatment. Because the only property that I used even in the previous proof, that the covariance matrix, how does it get rotated, and here is the orthonormality property. So as long as the matrix is orthonormal, that's fine, even if it's not a pure rotation, right? Okay, so now here's my strategy. In fact, I have to do no rotation. In fact, I don't even have to compute the other forms of the covariance matrix. In fact, I don't even have to do much at all, right? This is what I'll do. We do not need to rotate the image in any case. We just need to find the eigenvalues of A, and that's it. That is the rotated covariance matrix. Okay? So I can just decide on the eigenvalues of A. Everything has become like really simple now. I mean, the motivation was long, but the final algorithm is really simple. Okay, and this leads to the KLT corner detector algorithm. In the KLT corner detector, you go through all the image windows, you find the gradient in each window, okay, and you just find the covariance of that. I mean, you find the gradient times its transpose, the expected value of that, and find its eigenvalues. So you just find lambda 1 and lambda 2 and nothing else. And now if lambda 1 and lambda 2 are eigenvalues of the gradient covariance matrix, for a smooth patch, lambda 1 and lambda 2 should be close to 0. For an edge, one of them should be high, the other one should be low. And then for a corner, both should be high, right? And so really, the KLT criteria is that I look at the minimum of lambda 1 and lambda 2. If that's greater than some threshold, I'll say it's a corner. That's it. All right. So this is what it looks like. You have lambda 1 here on lambda 2 here in that axis. This dark gray region here, that's the flat region. Both lambda 1 and lambda 2 are below some threshold. Lambda 1 is much greater than lambda 2. I mean, lambda 1 is higher by some threshold than lambda 2. That's edge. Lambda 2 is higher than some lambda 1 value. That's an edge. But both lambda 1 and lambda 2 are higher than some threshold. That will be a corner. So that's kind of like the picture you get. Yes. The threshold is a threshold on the variance that you expect in your gradient, really, right? Because that's what lambda is actually depicting. It's depicting gradients in variance in the eigenvector directions. Did that make sense? Lambda 1 is the variance in the direction of the first eigenvector, and lambda 2 is the variance in the direction of the second eigenvector. So when I'm putting a threshold on lambda, I'm putting a threshold on acceptable variance. There is some variance in gradient, small ones, right, that I'm okay with. But if it's larger, then I'm saying it's corner. Yes, go ahead. Second question. Yeah, you still get it. Yeah. Okay, so here are the results. If I applied KLT algorithm on this image, I get these nice yellow dots at all the places. I ignore all the other places. It's actually simple synthetic data, but you have corners of all orientations and so on. And you do miss a few. That's fine. But it's actually pretty good that out of all the possible dots on this image, there could have been, these are the ones which are selected. Okay. Is this repeatable? Is there high repeatability in it? So here can you see the red dots in this image? Yeah. Okay. So I took an image sequence here. That's image 1, 2, 3, 4, 5, 6. I'm independently doing, there's no tracking happening. I'm independently doing KLT on each of the images. And you see that the dots, I get the same dots out the next time also. Okay. Right? So that's pretty good, because that, for example, now I can use these dots to find the fundamental matrix between these images if I want to, because they are like stable, they are sticking to where they are supposed to stick. All right. So I really like this algorithm because it's so simple and elegant. I have to do nothing really. I mean, I just have to compute this covariance matrix of gradient and find its eigenvalues. That's it. I mean, again, another example of elegant use of linear algebra that you see here. I mean, where did eigenvectors come from in this problem? But they really came from the fact that by doing phi transpose a phi, you get a diagonal only, which is the diagonal of the eigenvalues. So that means that's the appropriate rotation that you need. All right, some of the nice properties of this corner detector. Well, the first one I didn't say. It's really simple, so that's a nice property. Okay, but it's invariant to intensity shifts. If the overall image becomes brighter, these lambda 1, lambda 2 values are not going to change because they are variances. They don't depend on the absolute value. They depend on the variation of the gradient vector. Okay, The relative, they are invariant to intensity scaling. Even if it's not that I added, let's say, a value 100, a brightness value 100 to every pixel, but I just multiplied, so the image contrast stretched, right? It's a more higher contrast image than the original one. Even then, you can do the math here. Even then, that does not have any effect on the variance values. So really, to linear changes in image lighting, AI plus B type of changes to the image lighting, multiplicative and additive changes to image lighting, there is absolutely no effect to the KLT corner detector. It will give you exactly the same values. Yes. I don't understand your question at all, please. Yes. Yeah, that was the gradient mask. Yeah, the gradient mask itself is invariant to brightness changes, and so since this is working on gradient, so it is also invariant to brightness changes. You're right. Okay, so there was a question of what window size to choose in the beginning, right? So KLT corner detector is not invariant to image scale. What is happening here is that if this is really my roundish corner that you were discussing, right, and your window size is this small, well, you are at all these places you're going to say edge, right? But if it was at this scale, then you're going to say it's a corner. Okay, so your corner detector is typically not invariant to scale. It's also not invariant to scale because think of how you actually compute the gradients. The gradient themselves are computed by a mask, by a window, and so if the underlying data scales, that window may not be adequate to compute the gradients and so on, right? So this is not a very nice property of edge detectors or corner detectors. But how did we deal with in edge detection? Well, I could try multiple scales, so I could do the same here. Yeah.
Sir, the last one, that it's not invariant to color and brightness. So can this pattern be used for matching?
Yes. That's what makes it a more stable corner detector. So which means the more repeatable it is, the more distinctive it is, the more easy it's going to be matching, right? Okay, so this is the problem of scale. What people sometimes do is they try a lot of different scale windows while doing the same corner detection. So they do a window this big and a window this big and a window this big and find corners from all of them, and then they merge them together and they say all of these points are corners. Okay, but it is a problem. I mean, this thing on a smaller scale will be a corner and not on the larger scale. This thing on a larger scale will be a corner and not on a smaller scale. So you will so that's why you do multi-scale processing. So there are many scale invariant corner detectors. In fact, you can think of it as motivation. We'll look at one scale invariant corner detector, which is very, very popular. It's called SIFT, scale invariant feature transform, where it's not just like KLT is rotation invariant. It's intensity changes invariant and so on, but it's not scale invariant, and we'll see that there are some feature detectors which are also scale invariant. Okay, but essentially if you have an algorithm which is not scale invariant, typically you try it at different scales. You try different scale values to find your corners. Yeah. Yes. So those are affine changes in intensity. Yeah. So it's invariant to that. Okay. So now we have a corner detector on our hands. Okay. Let's see how I can use that to make panoramas. Okay. You already know how to make a panorama if somebody were to give you matches. Okay. So the real question is matches. Okay. So why do we want to make panoramas? Well, it's a nicer picture. If I'm looking at just this house as opposed to this scene, well, that's a nicer picture. I get more wide angle views even from a narrow field of view camera. Okay, so this is approximately this picture. So this picture is typically the field of view of a consumer camera. This picture is typically the field of view of humans. This picture is even more than that. It's a 360-degree panorama, right? 360 degree horizontally. That's why straight lines are not mapping to straight lines, because they've mapped it onto a cylinder and then unrolled the cylindrical surface. Okay, but human vision is also pretty panoramic. We typically have, like they say here, 135 degree, some people say up to 150 degree. That's the field of view that people mostly have. There's a disease of the eyes which is called glaucoma, where your field of view starts to narrow. It happens typically after 40 years of age. So I have to be careful. And actually it's hereditary, so it runs in the genes and so on. But the field of view narrows and narrows and narrows, and in extreme cases it can become so narrow that it leads to blindness. Okay. All right. So what's the first step if I want to make panorama? I have two images here of this building, and I find KLT corners in the first one, and I can find KLT corners in the second one, and I have some 368 corners in this image that I detected by some threshold of KLT. If I were to lower that threshold, I'll get more corners, right? So I have some 368 corners here and some 498 corners here. How come so much more here? Because this portion of the building was not visible here, and that has a lot of windows, and so I found a lot of corners around that. Notice my corners are pretty nice, right? They are actually corners. They're not like theoretical corners, they're like physical world corners also. Not in the sense of image processing corners, but also in the sense of what a normal person would call a corner. Okay. All right. So now the key task is I want to establish correspondence for this corner detector. So once we have corner points in both images, we need to establish their correspondence. And we saw this picture before. If my corner detector is repeatable, which means it gives me the same features, the same physical features in the second image also, then it would be easier for me to find correspondence. Okay, but if I pick one image, one corner point here, which one of the four is it in the other? I need to solve that problem now. Okay, so some sort of match matrix, so that after I am done with that matching, I have something like this. Okay, there were a lot of other possible matches. In fact, there were n square matches here. There were 16 possible matches that I could have done here, but I have to pick 4 out of those. Okay. All right. Now this is not an easy problem. Okay, because there are a lot of problems in images, and one of them is self-similarity. So here what we are showing is this is like a corner detector output from one image. And this is the second image, and that's the corner detector output of that. Okay. Now, if I take each of these patches, I mean, this looks like you kind of know when you're looking at it of, okay, what should match to what. Okay. But if you look at each patch, I mean, take a small neighborhood around it and plot it. These are all those patches here for the left image, and these are all those patches here for the right image. And that's really the question that you have, that, okay, I pick this patch here, which one is it out of those? Okay. And that's not an easy problem. In fact, it's also not easy because, well, one thing, there's self-similarity. So all these patches kind of look the same. Okay. But also because the actual overlap between these two images is just about here. It's not anywhere else. This corner might look very similar to that corner, but actually that's not a match, right? That's the left side of the building and that's the right side of the atrium. So, okay. I'm just showing this as I forgot to put the reference here. I'd put that in the slides before I share. This slide is by Aloysius Efros, who was at CMU and now he's at Berkeley. But this is a very good illustration of highlighting why matching is a problem. Okay. Okay. So how do you match between, let's say, a patch here and a patch there? How do you do that matching? Well, if you call this patch F and you call this patch G, then we have been doing this, you could actually find their L2 norm, the sum of square differences between them. If this is low, then the patches are likely similar. If this is high, the patches are not similar. So this is called L2 norm, or sum of square differences. Or you could find some other distance measure like L1 norm, which is the sum of absolute differences. Yeah. Yeah. Let me proceed. I'm going to show you what we do with this, right? I just showed you as an example to motivate that it's a hard problem. Okay. All right. So Just hold the question for a moment. I'll take questions towards the end. Okay. So we are expecting lighting variations maybe in our scene. If we are expecting that, I need a distance measure which also kind of caters to that. And one very good distance measure is actually the correlation coefficient, something we were talking about earlier in the slides. Correlation coefficient has this definition: rho between f and g, two vectors f and g, is f minus, oh, there's a bar missing here, sorry, f minus f bar. Is it missing? Yeah. F minus f bar, g minus g bar, the sum of that, which means what do? I take the f patch and subtract its mean from every pixel. I take the g patch and subtract its mean from every pixel. Then I take their dot product, point by point multiplication and addition. That's dot product. Dot product of the mean subtracted vectors. That's the covariance term divided by the variance of the f patch, the variance of the g patch. The denominator terms are nothing but variances. Okay? So this is the definition of correlation coefficient. It's a measure that varies between +1 and -1. And if it is 0, the patches are completely not matching. They are completely uncorrelated. If it is a high positive number or a high negative number, in both cases, the patches are matching, except if it's a high positive number, then high positive decimal, then that means that they are matching with positive correlation. They are similar in color. If f is high, g is also high. And if they are negative, then that means their relationship is reversed. If f is high, g is low, but they still have a strong correlation between them. Okay. This measure, by the way, has some nice properties. It's between +1 and -1. +1 implies perfect positive correlation. -1 implies perfect negative correlation. 0 means absence of any correlation. And then the correlation coefficient is invariant to affine intensity changes, which means if f is multiplied by af plus b and g is also multiplied by cf plus d, the value of correlation coefficient will not change exactly, because it's actually a measure of the strength of linear relationship, and you still have a linear relationship because you transform the intensities linearly. Okay, so it's a very nice measure. It has some nice properties. Okay, all right. So there are lots and lots of other distance measures. There is like an infinite number of them. Literally, they are infinite. Okay, so you could use your a distance metric that suits you well. Okay, I've just shown you 3. Okay, all right. So now I'm back to this problem. Okay, I know how to match a patch with patch. How do I establish correspondence? Well, once I establish the distance between all pairs of points. So this is like an n square matching now. If I have n points here, n points here, I just do these n square, all the distances of the distance measure of my choice. Okay, but I still have to pick pairs out of this, which will minimize this combined matching somehow. Okay, so the simplest thing that you can do is this exhaustive strategy that I'm showing you. What is exhaustive? I have points in the first image, I'm calling them A, and I have points in the second image, I'm calling them J, and I've matched each one to each one using the distance measures that I showed you. Now, how do I find like a minimal set out of these? Okay, yeah. So yeah, not the spanning tree. This problem in theoretical computer science is called bipartite graph matching. This is the same problem you have if you have a bunch of males and a bunch of females, or आपने उनकी शादी करानी हो, right? So you could find some distance measure between all of them, and then try to optimize, and then have a grand wedding. This is called bipartite graph matching problem. Okay, so there is a greedy solution to this, which is very simple. I can pick the best match out of all of those first, and then take those 2 points out of the equation, and then pick the next best match, and take those 2 points out of the equation, and so on. Okay, that's greedy. That's not guaranteed to minimize the overall cost of the matches. So it's not a very good strategy, even though it's very simple. The optimal strategy so the greedy solution may not optimize very well the overall cost of the match. The overall cost of the match is the final pairs that I pick, what's their cost, the sum of their cost, right? So I want to minimize that. And there is an algorithm to do that. It's called the Hungarian algorithm. Hungarian algorithm gives you the optimal solution to the bipartite graph matching. Okay. I'm not going to discuss Hungarian algorithm. It just exists. You can go look it up. I'm just pointing you that that's the optimal solution, or you can settle for a greedy solution, which is non-optimal. Okay, so this strategy was exhaustive search. For each feature in one image, look at all of the features in the second image, use Hungarian algorithm to find a good set of patches. People do other things. People do hashing. From the descriptor, I compute some sort of short descriptor, and then I speed up my search through hashing functions. Nearest neighbor techniques, I build, let's say, k nearest neighbors, or two best matches for each point. I store them and then try to minimize the overall cost and so on. So in this problem, what am I going to do? I'm going to skip maybe one or two. I'm going to skip these one or two slides. You can look at them. These are the distributions of nearest matches. But what they did was they out of all the red dots, the blue ones are the nearest match. For every point, I find which is the nearest matching point, and for those, I've picked up a subset of those where the nearest match is actually much more distinctive than the second nearest match. Okay, that's actually a very interesting statistic that was proposed by David Lowe, the same guy who came up with SIFT algorithm. He said one good way to pick out of all these red points, one good way to pick a pair is pick that one whose best match in the other image has much better cost than the second best match. Then that means this point is distinctive. It has something unique in it. Okay, so the blue ones here are distinctive points, and notice that it's not accidental that they are not coming on the left wall or the right wall. They are coming in the overlap area. Okay, but I still have a problem. I mean, it's still quite messy, and so what is the next thing that I should do? Ransack. Yeah. So this is an example for SSE building. These are top 20 matches in my data set. These are top 100 matches. Now notice that in the top 100 matches, I have some wrong matches. This corner of the window matched here somewhere with this corner. Okay, it's not the same match. So that you see those lines going in wrong directions. They are wrong matches. The lines going in roughly the horizontal direction because that's how the camera had moved. Those are the correct matches actually. Okay, so I have some outliers typically, and our outlier rejection strategy of choice is ransack. So this is what we do. We compute the minimals. What is the minimal set here? 4 pairs. Out of those noisy pairs that I have, 4 pairs as minimal. So I pick 4 at random. I compute H from those 4 pairs. I find consistent set from the rest of the pairs. How do I do that? I have an H now. I take all those points in the left image, transform them to the right image, and see whether they lie close to their matching point. If they do, they are inlier, otherwise they are outlier. So I compute my consistent set like that, and if the consistent set is larger than the previous best result, I mark this as the best result so far. I recompute H using all the points in the consistent set, and I keep repeating this. All right? That's exactly what ransack is. So what do I get? In this case, out of those blue points, when I apply ransack, I get these yellow pairs. Now, if you look closely, can you look closely? Yeah. If you look closely, they are quite interesting. You see there is a yellow point here. Okay. Now that yellow point is here because this was like a T of that bar, right? The banister which is there to protect from you falling over, right? So it was the T of that, and that's a distinctive point because you have a similarity in the other image, and those were picked up by the ransack algorithm as inliers. Okay, and similarly, if you look at it, all the yellow points are in the overlap area. There's no like yellow from here to here because you were unable to see those matches. So these are the matches picked up by the ransack algorithm, and now you can estimate the homography. Once you have the homography, you can use this as the base image and warp this image by the homography onto this image, and this is the result you get. All the rest of the steps you are already familiar with because you have seen them. The matching part is really what is unique here. Yeah. Sorry, I can't figure out which one you are pointing to. Yeah. This and this, yeah. 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 Well, why did the homography exist? Yes, indeed, these walls are not on the same plane as that, but we are not using homography here because this is a planar structure. We are using homography here because the camera only rotated, right? So in the camera rotation only case, the structure doesn't have to be planar, and indeed the image stitches well with the homography. How do you know it stitches well? Well, now straight lines are straight lines, right? Look at this bar here. It has come into a straight line where it is nowhere close to a straight line here. And so that tells you that the homography is decent. This line is straight and this line is straight, and they are converging to what seems like a reasonable vanishing point. All right. Let me stop here. There's just one last thing I wanted to do. How do you warp multiple images and how do you stitch them together? So I'll discuss that at the beginning of next lecture. Yes, go ahead. Questions? Sorry, I can't understand. Homography does what? Yeah. Reflection is just multiplication. It could if you had a bunch of wrong matches and you thought that was the correct transformation, it could, but it didn't happen in this case. It's actually, see the power of this. When I showed you those patches in the beginning as motivation, it is a pretty hard problem, right? Taking all those gray patches on this side and gray patches on this side and seeing where is the match. But now we have built enough powerful tools, including KLT algorithm, including this matching strategy, and then filtering out the outliers with Ransack. We have built enough tools now that we can solve that really hard problem which I showed you before. Okay. In fact, this is how people make panoramas in phones. You have this panorama filter with your camera. This is how panoramas are made. All right. Any further questions? Yes.
Once you identify your corners, could you have increased the window size where the matches would be, if they were matching, it would be more likely if they were the same?
It doesn't have to be that the window used to identify the corner and the window used to actually conduct the match is the same. In fact, it doesn't even have to be that you use the same window for the same pixel data for the match, right? In one of the very early slides yesterday, when I was motivating this problem, I said there is a feature location and then there is a feature descriptor. So in this case, the pixel values within the window are the feature descriptor because I'm just correlating them or I'm just doing sum of square differences. But as we will see tomorrow, inshallah, the feature descriptor can be a lot more complicated than that. And the descriptor is needed when you want to do the match. Okay, so when we look at SIFT algorithm, they used a much more complicated feature descriptor than just using the raw pixel values like the match here. They did a much more complicated feature descriptor than that, and that is extremely powerful. That's the sort of descriptor that allows you to match in. Remember, I showed you the SFM problem. They just downloaded images from the internet of Rome, right? And now you have to find matches between these pictures. A very simple strategy like this is unlikely to work because the images are so different. They are not taken by the same camera. They are not in the same lighting condition, day and night. There are lots of variations there, scale variations and everything. So to be able to do that sort of very difficult matching, raw pixel values are not going to be enough. All right, we'll stop here. Remember, tomorrow is Thursday, so on Thursdays we have quizzes. So we'll have a quiz tomorrow, inshallah, which will cover till the previous module's end, right? Stereo, SFM, camera models, all of that. So that's what the quiz covers.